welcome back to the last lecture of mine. So this is the formula from yesterday. So yesterday we learned that for the Q-T-SIP with step initial condition, the generating function for the Q Laplace transform for the position of so n means that now we are considering step initial condition. And now, sorry, there's an inconsistency with passive case, but now we are denoting the nth particle position by xn of t. Then this Q deformed Laplace transform can be written as n-fold integral given in this way, right? And the pi tilde is given by this. One small remark here is that, yes, in this lecture, whole lectures, we are focusing on this step initial condition, but by changing this function, one can study discrete time, Q-T-SIP, and some other initial conditions. And in particular, in the paper I mentioned yesterday, we could consider the case where this pi function is generalized in this way with one parameter added. Then by using this parameter, one can study stationary case of Q-T-SIP. Okay. So this is just one remark. Yeah, as I said, for the case of Q-T-SIP, the random initial condition has some difficulty of divergent moment, but in this way, such difficulty does not appear because we don't use any Q moments, right? Right. And then, yeah, sorry. And what I told you yesterday was that even though this looks pretty complicated, one can apply the Cauchy determinant identity, in particular version for theta function. Then we can rewrite this as an integral, multiple integral of a product of two determinants. Then one can basically apply the usual techniques from random matrix theory or determinant point process to arrive at the Fredholm determinant formula. Right? Then with this formula, one can do asymptotics to see universal behavior. And a good point of this approach is that one can take always Q equal zero limit, tacit limit. And then you can see what happens easily. But maybe at this point, we can consider a slight generalization of the Q equals 0 case. Yeah, if you take Q equals 0, from pi we get this Vandermonde square, and then yeah, all Q product becomes just a simple product, right? And this pi theta function can be considered can be written as a product of some function. And for the original TASEP case with the step initial condition, this is just again e to the power zt. But maybe yeah, as in the case of stationary Q-T-SIP, we could consider some generalization. For example, something like this. We could put some more parameters, but yeah. Okay. And anyway, what I want to say here is that if we see this kind of structure, one can already apply the standard machinery of determinant point process, free fermion, because from here you see already a product of two determinants. So just as in the case of yesterday, we can write this as an integral of the product of two determinants. Then one can proceed. Right? Right. So yeah. Okay. then today, up to now, we have been concentrating on just single species process. It's usually A-safe, acute A-safe, and so on. All of them are just single species processes. But now there are some interest in multi-species models, multi-state case. And today I want to explain one of them. Yeah. So basically, my lecture today is based on one paper from last year. So this is a collaboration with my student Hiki and people from Melbourne. For the moment, there is only a paper which is just a kind of announcement of the results, which appeared in physical review letters. We are still writing the longer version, which should be coming soon. But anyway, but I think, in fact, the analysis is not so difficult, not so different from the passive case. So once you listen to the lecture today, probably you can understand what one should do, at least for the analysis part. And so there are several kinds of multi-species generalization of ASEC and so on. But in today's lecture, we focus on one particular case. So the model itself was introduced by Arndt, Heinze, and Rittenberg. So this model has not been studied so much, but I think this is very, very good model from various points of view. And we call this AHR model in this lecture. Again, this is a one-dimensional exclusion process on Z. So this is the exclusion process. So on each lattice, there could be only one particle. And now we have two species of particles, which we call plus and minus particles. So they are distributed in some way. Right? And the plus particles are basically tacet particles, hopping only to the right with rate beta. If there are plus particles, yes, they hop. Minus particles are also like space-safe particles, hopping only to the left in the opposite direction with rate alpha. But of course, we have to introduce some exchange or interaction mechanism between plus and minus particles. So the interaction is that if plus particle and minus particles are on the neighboring sites in this order like this, then they swap their position with rate 1. So in this way, so plus particles hop only in the right direction, minus particles hop only in the left direction, and there are some exchanges when they meet. Right? Is the model clear? Okay. Yes.
So if particle, like when they swap, they don't like you don't jump to the left and straight out. You swap straight one instead.
So after this swap, this just becomes this. No. So yeah. This is the exclusion process. So at each lattice site, there could be only one particle. Yeah. Right? Is the model clear now? Okay. Yeah. I don't know if do they make a difference? It's just an interpretation, right? So, yeah. The rule is that when they in this position, plus or minus, on the neighboring sites, they swap the position. That's it. Yeah, with rate on, yeah.
And they only swap in one direction?
Yes. Later I mentioned that in so yeah, that's possible in fact. I mentioned a little bit about backward swap. Okay, but in today's lecture, basically we just focus on this particular case. Right. Yeah. So this is still no, this is not for. So this is for the morning lecture by Paul, right? So is it okay? Yeah, now we have some non-equilibrium system. What we do first, as in the case of ASF, first thing to do is to try to find some stationary measure, stationary non-equilibrium stationary state. And in general, it's not so easy to construct the stationary measure for this process. But it is known that this can be achieved by using so-called matrix product ansatz. On periodic, well, basically on periodic case, I think one should be able to take system size infinity limit, but I don't know if somebody has really worked it out. But at least for the case of periodic lattice system, periodic initial condition case, there is a kind of known procedure to construct stationary measure of this process for general parameter in the form of a product of some matrices. Okay? And this method works, in fact, for the case with reverse exchange. So yeah, in this generalized setting, there's also a swap when two particles, minus particle and plus particles, are on neighboring sides with this order. So the order is different now, right? So in this case, we can postulate that there's a swap again with different rate Q. Yeah. Even for this case, for periodic lattice, there's a known procedure called matrix product method to have the exact stationary measure. Okay, but this is already pretty complicated. So, but there's one special case which is much simpler, namely when these parameters alpha and beta satisfy this condition, alpha plus beta equal 1, then product measure, so all sides are independent, and each site is occupied by plus, minus, or empty, independently with some probability. Right? So now we are considering kind of tensor product space. At each side we have three-dimensional space, C3, and we are considering infinite tensor product. And at each side, maybe we label the three-dimensional space by as corresponding to plus particle, minus particle, and whole. And this means that at each all sides are independent, and at each lattice site, the site is occupied by plus particle with probability rho plus, by a minus particle with probability rho minus, and it's empty with probability 1 minus rho plus minus rho minus. Of course, they should satisfy non-negativity condition. Yeah. So this is now very similar to the case of single species ASF. In the case of single ASF, we already learned that the product Bernoulli measure is the stationary measure, and you know how to prove it. Right? So this is the exercise of today. So to show that this product measure is the stationary measure for the case with this condition. Yeah. So most of the part of our analysis can be applied for general alpha and beta which satisfies this condition. But in most cases, at least in this lecture, we take the kind of symmetric case where we have alpha equal beta equal 1 half. Yeah. In the following. Then what do we do? As in the case of single species case, we are very interested in currents, especially for this stationary measure. And this is very easy. So this product measure with the 2 parameters rho plus rho minus is denoted by this thing, rho plus rho minus. And in this case, what is the current? So this is a function of rho plus rho minus. Can you write them down immediately? Okay. Yeah, so this is pretty easy, right? So when do we have current for plus particle? Of course, in this case and in this case. And in this case, we have this happens with probability minus, and the rate is 1 half. And this happens with the probability rho plus rho minus with rate 1. So this is the current for the plus particle. And the for minus particle, it's basically the same. It's given by this. Once we have this expression for the current, then one can write down the hydrodynamic equation in the Euler scale. It's just a continuity equation, right? For two. Okay, sorry, maybe the notation is not so optimal. So now you have to think that this is a kind of function which depends on macroscopic time and position, space. But anyways, yeah, this is the hydrodynamic equation. And here you have to substitute these expressions into here, J plus and J minus. So this is a evolution equation for rho plus rho minus. Of course, in the single species case, so for TSF, this was Bargall's equation. So in that sense, this it may be called two component Bargall's equation. But for this particular case, there was some previous work by Delogs. So this is also sometimes called Delogs system. And for proceeding further, we specify some initial conditions. And as in the case of ASEF, we still consider some rather simple initial condition, which is some kind of generalization of step initial condition again. In this lecture, we focus on very particular case of step initial condition in which on the left half of the lattice, we have only plus particles with density rho. So all sides are again independent, and they are put with probability rho at each side. And on the right side, all sides are occupied by minus particles, as in the case of single species cases. So we sometimes call this rho 1 initial condition. So this terminology appears many times in the exercise, so you should recall it, right? So this initial condition we call rho 1 initial condition in this lecture. So one more comment is that so this system was also studied by Fritz and Toth. Okay. And now maybe we are interested in solutions for the hydrodynamic equation for this particular initial condition. Okay, yeah, sorry. So this is a microscopic initial condition, but there's an obvious macroscopic version. At time t equals 0, we should have value rho to the left for the plus component and density 1 for minus particle to the right. So we are interested in the solution of this two-component Poisson equation for this particular initial condition. And in fact, this can be solved explicitly. And in rather general case, this kind of problem with strict initial condition for this type of hydrodynamics is called Riemann problem. And there's a kind of standard procedure to construct a solution. And it works well for our case. And yeah, but this is already pretty complicated, so maybe I don't write down the whole case, but one can write down some solution explicitly. And from this solution, sorry, I want to skip this. In particular, we can consider what is the density and the current at the origin. Yeah. Later, we focus on the current around the origin, at the origin for plus and minus particles. So we are interested in macroscopic state around the origin. So from this solution for the two-component Poisson equation, for this particular initial condition, we see that they become already a little bit complicated, but one can do the calculations explicitly. And the values of densities and currents at the origin are given by this expression. So this is a kind of generalization of the task. For the case of TSF, the density at the origin was 1/2, and the current was 1/4, right? And these are the kind of generalizations of these simple facts for TSF. So about the hydrodynamic behavior, one can really study what's happening by using this kind of solution. But we are interested in fluctuations and correlations and so on, as in the case of ASIC and so on. Yeah. How can we try to study such fluctuation properties of this microscopic model? Yeah, if you recall again the case of ASIC, so we had as a hydrodynamic equation, the Poisson equation, right? And at some point, I mentioned that, of course, for the case of TSF, we can really study the fluctuations exactly. But in fact, it turns out to be the same as considering noisy version of the Poisson equation with also diffusion term, right? And then from this one can also see, so this is equivalent to the KP equation. And if you do the analysis, one sees that the same universal distribution function, Grace-Wiedemann distribution, appears. So for the case of two-component system, maybe one can try to do something similar. Now we have hydrodynamic equations. Maybe it's difficult to study microscopic model now, but maybe one can try to see if there are something one can say about the fluctuation of the microscopic model by considering the equation with noise. So this is an idea behind the nonlinear fluctuating hydrodynamics. Yeah, so the naming is very simple, right? So we are considering hydrodynamic equation, and now we are interested in fluctuation. So we add noise. So this is called fluctuating hydrodynamics. Yeah. And because we have to include some nonlinear nature coming from the Varga's nonlinearity, so this is the nonlinear fluctuating hydrodynamics. Yeah, in physics, in fact, linear fluctuating hydrodynamics have been considered for a long time, starting from the book of Landau, Lifshitz, and so on. But nonlinear version is usually difficult, but especially for one-dimensional case, there are many nice progress recently. Right. Now, yeah, I started from very particular case of two-component microscopic model, two-component, two-species task-safe. But now maybe we can consider rather generic one-dimensional systems with multi-component. And we assume that hydrodynamics is written in that, can be written in that form. So as an example, of course, we can think of this AHR model. But in fact, the primary application of this theory, nonlinear fluctuating hydrodynamics, is not for stochastic dynamics, but for Hamiltonian dynamics. If you remember the first lecture of mine on the first day, on Monday, I explained about Newton's dynamics, and we're interested in fluctuation behavior of Hamiltonian dynamics, right? And the three-dimensional case is most important and interesting, but it's, for the moment it seems almost impossible. But maybe one-dimensional case is easier. And as an example, I explained a little bit about particles which are connected by nonlinear springs. The most famous one is the FPU, Fermi-Pascal-Lamb chain. Right? And in this case, because this is a Hamiltonian system, it is well known that there are three conserved quantities: particles, numbers, basically density, momentum, and energy. And in this sense, we can consider three-component systems. And even for this kind of Hamiltonian dynamics, at least at the level of hydrodynamics, at least one can do many things. One can write down this kind of equation and study some properties. But the fluctuations are very, very difficult, in particular for this Hamiltonian dynamics. But at this level, there's no big difference between Hamiltonian dynamics and stochastic lattice class like AHR. So maybe one can treat them on an equal footing, right? Then to study fluctuations of these systems, maybe we can simply try to add noise. Sorry, but before adding noise, there are something we can do and we have to do. So this is a little bit too general. And in many cases, we consider the situation in which system is in rather close to equilibrium situation, and with the density rho 0 vector. Okay, sorry. Okay. Then so density field here, which in fact depends on x and t, are considered to be expanded around this specific point in this way. Right? And we are basically interested in this kind of variation from this fixed density. And what happens for the current? Current is, as in the case of AHR, thought of as a function of density field. And now we do this expansion, not expansion, yeah, this perturbation from rho 0. So then we have this. Then we think that, so basically the current is like the current for this rho 0. But now we have the first order term, which is now linear in U, where this A is a matrix. Simply given by this Jacobian for current with respect to density. Yeah, sorry, so this is a trivial rewriting, but let me write down. So, but you should keep some space here. So if we expand this current only up to this first order, then this hydrodynamic equation is very, very simple, becomes linear. As an equation for U, the equation becomes simply this one. Right? And now, as I said, we are thinking a situation in which the situation, the system is almost in equilibrium. So we are thinking that A can be considered as constant. Then this is very, very simple equation. So all we have to do is to try to diagonalize this matrix A. And yeah, this is what we do. So yeah, in general, this can be diagonalized by some matrix. There's some mistake, I think. So the diagonal matrix is denoted by capital lambda, and we are thinking that this is a diagonal matrix with eigenvalue Ci. So, right. And then, yeah, now I'm doing a very, very simple thing. For this diagonalized component, which is denoted by phi here, the equation becomes decoupled completely. So in component, the equation looks like this, and you can immediately see that So for this phi function, this is some function which propagates with a definite speed c alpha for each component. So they are just moving with speed c alpha. And yeah, so we call this, so U are kind of original component mode, but after this diagonalization, we call this normal mode. So each normal mode propagates with definite speed c alpha. Very easy. At this point. So if this is just enough to study many properties of the original microscopic model, the story was very simple. But this is like a linear fluctuating hydrodynamics. But in many cases, especially in one dimension, this story is not enough. In particular, if we look at some fluctuation, there are some experiments, numerical simulation, some evidences that this is not enough. So we have to go further, right? We have to include some nonlinear effects, but yeah, as you have kept some space here, a simple way to include nonlinear effects is to go to the second order in this expansion, right? It's very simple. So let's do that. We call this Hessian matrix to be H. So up to this was a first order. And now we are considering second order. But this is just simple at this point. Yeah, instead of the equation above, the linear equation above, we now have to consider this nonlinear equation. But first, maybe this part does not change from the first order case. Maybe we can still try to switch to normal modes by using the same matrix R. Yeah, this part is a little bit cumbersome, but this is something you have to do here. Now the coefficient H alpha beta gamma is also written for the normal modes. And now the coefficients are denoted by the character G. And this is just a transformation of H using alpha. Expressions are a little bit complicated. Yeah, conceptually, of course, it's not very difficult. Yeah, anyway, if we go to the second order, if we switch to the normal modes, this is the equation. But so at this point, we haven't added the noise, so we cannot really study the fluctuation effects. But now we can add noise and also diffusion term, as in the case of single species case. So this is the noise term, and this is the diffusion term, as in the case of KPZ, single species KPZ equation. Yeah, so this is the equation. Now, if you look at this equation, of course, this is very, very similar to this KPZ equation, right? Yeah, as I already mentioned, yeah, by shifting u a little bit, this can be seen like this. So then this is already almost equivalent. But of course, there are some nonlinear coupling here. So this may cause serious difference from the single component case. But naively, as I said, for this part, basically each mode is propagating with definite speed, right? So if we are only interested in large T behavior, large scale behavior, then maybe normal modes can be considered as almost decoupled, which means that maybe we can simply focusing on the diagonal part of this nonlinear for this nonlinear term, and simply replace by this. Of course, this is not at all rigorous, right? So this is just a naive expectation. But if we do this, if we also think that they can be also considered as diagonalized for normal modes, then this is exactly the KPZ equation for single component case. Of course, there's a shift, but this you can do always easily by the Galilei transform. Right. Anyway, in this way, yeah, now one can make rather concrete conjecture for multi-component microscopic systems. Right? If we assume this is kind of correct, then for very generic one-dimensional systems, including Hamiltonian dynamics, if we look at this normal mode, fluctuation properties are expected to be described by single species KPZ equation. So this is the basic idea of nonlinear fluctuating hydrodynamics. So this is. How? Yeah, sorry, yeah, I didn't mention very important thing, thank you. Of course, so this argument strongly depends on what kind of G matrix they are. And in some cases, in particular for important, of course, one of the most important cases is Hamiltonian dynamics. In this case, because of this symmetry for Hamiltonian dynamics in general, so we have now 3 modes, and for the one mode, nonlinear, so this term vanishes. Then what I said that each mode is like KPZ becomes completely wrong. So now we have to consider something different. Yeah. Sorry, yeah. So yeah, in particular for Hamiltonian dynamics, which is very, very important. And yeah, this is not completely correct. Yeah, we have to consider this carefully. But for generic, very generic case, so this is the simplest conjecture. Okay, thank you. So now we have some rather concrete conjecture for multi-component microscopic dynamics. Right? And yeah, after this conjecture, there have been many numerical simulations and so on, which almost, which are very consistent with this prediction. So even for Hamiltonian dynamics, like FPU chain, so one can do numerical simulations on computers, right? And then they study normal modes and try to see the fluctuation. And then they can compare with the KPZ predictions, and they are matching pretty well. That's fine. But of course, it would be nice if we could prove it mathematically. But in particular for Hamiltonian dynamics, that would be great, I think. But that would be very, very difficult because so Hamiltonian dynamics, if it is not integrable, there's almost no chance that one can do very asymptotics and so on to study large T behavior. So I still think that this is a very interesting and important open problem, but that may be too difficult for the moment. But as I said, so this formulation can be applied not only to Hamiltonian dynamics, but also to stochastic dynamics, like AHR. And one can make this kind of conjecture for stochastic dynamics as well. And then for stochastic dynamics, there's not a real serious difficulty like chaos, which is there for Hamiltonian dynamics, right? So there's a better chance that one can really prove this kind of conjectures for stochastic dynamics. But this has not been done. But yeah, what I want to say is that at least for this AHR, one can do something. Right. Now we can simply try to apply this general scheme to the case of our AHR, in particular for our step rho 1 initial condition. So A matrix is easy, and so this you have to calculate. So this is exercise. So this is easy. Okay. So another thing. Today maybe it's not so important, but let me mention one more thing. Right. In the theory of fluctuating hydrodynamics, especially to study the KPZ scaling, it is also useful to consider the equilibrium correlation, so-called susceptibility matrix. So this is the covariance of the occupation numbers for the processes. For the case of AHR, so at each lattice, you should think that eta plus is 0 if there is a particle at the site, and 0, if plus particle is not there. And eta minus variable takes value 1 if there is a minus particle at the site, and takes the value 0 if minus particle is not there at the site. And for this for this variable, in the space measure, they are random variable, and one can simply calculate this covariance matrix. And this is C matrix, and one can also calculate this. So this is also in the exercise. I think this is so this is also in the exercise, right? Because this comes with a star mark, you don't really have to calculate, but yeah, it's not so difficult, so you can just try. Okay, once you are given, so in general, this depends on rho plus and rho minus, but we can specify to our specific case of rho 1 initial condition. Then this is some given matrix, 2 by 2 matrix, which can be diagonalized like this. Then somehow I give you the matrix R explicitly. For our particular case of rho 1 initial condition at the origin, the R matrix can be calculated to be this. So this you can also try to check in the exercise. So yeah, for this concrete case, one can check that this becomes diagonalized, right? And you can also calculate this. Right. And one can also calculate kind of susceptibility for the normal mode. And this is also normalized. Sorry, diagonalized. You can also try to calculate them. Right. Yeah, these are just simple exercises of this general theory to the case of AHR. But yeah, now from this generalized conjecture, we can make a specific conjecture for the AHR model. Right. So there are now two normal modes. One mode, we call it S minus. Maybe I write S minus. And N means the, sorry. Sorry. Yeah, I didn't specify that. So in the initial conditions, all plus particles are on the left side, and all minus particles are on the right side. And then, as in the basically as in the case of single species ASEP, we count the number of particles which cross the origin up to time t. And now we have two species of particles, and the number of plus particles which cross the origins is denoted by n plus of t, and the number of minus particles which cross the origin up to time t is denoted by n minus. Yeah. So basically, conceptually it is simple to consider what kind of conjecture we should make. Right? Yeah, we should look at normal mode, and then we are considering step initial condition. So if we look at the current, it should be given by GU trace rhythm distribution. Basically, this is the message, right, of this equation. But concretely, how to define this scaled version of the current is not completely trivial, but conceptually it's easy. So this we have to consider the normal mode. And so this is given by So this is this this should okay. So this should come here. So this corresponds to plus particle current. This corresponds to minus particle current, and we should consider normal mode, right? So as I wrote down, so this corresponds to considering this and this one, right? So now we are considering normal mode, so we have to use this matrix R. So this is why we have to consider this kind of combination. And then, so we have to subtract the kind of average behavior. Average current was written down somewhere near the origin. So if you calculate a little, well, okay, so maybe I don't have to calculate. So for J minus. And then let me try to write down the correct formula, at least for this mode. Yeah, so of course this is KPZ scaling, so we always, as usual, we have t to the 1/3 here, but the coefficient looks pretty ugly here, right? But in fact, it's not so difficult by using this kind of coefficients appearing in these calculations. One can, and also here, one can see how we should take these values. So there's a kind of standard way, so-called KPZ scaling theory, which determines this coefficient. But anyway, so this is a kind of normal mode for our particular case. And then, so this is a kind of normal mode, scaled version of the normal mode for one mode. And then in the t goes to infinity limit, we expect to see the GUE trace rhythm distribution. This is a conjecture. And of course, we should have another conjecture for another mode. But because of this random nature, in fact, for this mode, we expect to see Gaussian distribution. So in this case, yeah, I don't write down them explicitly. If you're interested, you can take a look at my paper. Now we have considering Gaussian fluctuations, so we should divide by square root of t. But anyway, so yeah, for this mode we expect to see Gaussian. So this is the original conjecture from fluctuating hydrodynamics. But in fact, for our later purpose, in fact, it is easy. It is useful to make the conjecture a bit stronger in the sense that this is for each mode, right? But we are basically thinking that all modes are independent. Maybe we can consider slightly generalized conjecture for the joint distribution, which so this joint distribution for the scaled normal modes tends to the product of trace rhythm distribution and Gaussian error function, Gaussian distribution. So this is the slightly generalized conjecture. In fact, in the paper, so this theory was first anticipated by, sorry, no, anticipated by, sorry, the Dutch guy. No. Who was that? Dutch guy. Sorry, so I forgot the name. And formulated in a better way by Spohn. And yeah, he only mentioned this conjecture for each mode. And yeah, so this he was saying that yeah, somehow he didn't think about this kind of joint version, but this should be slightly more say strong. We should, yeah. This is a slightly better version of formulation of this conjecture. Anyway, so this is the conjecture. And we want to. Okay. Hmm? Yeah, that's right. Yeah, Hank Mayer. Yeah. That's right. This is the guy who anticipated conjecture. Yes. Yes. So this is basically the fact that each mode becomes a single component capability. This is just fine for this case. But now we are considering random initial condition here, right? And even for single component case, if we have some random initial condition, depending on the position, sometimes we see place-width distribution. At other place, we see Gaussian behavior. Yeah. Because effect of the initial condition is too strong, and this is happening for this mode in our case. Okay. Yeah, for example, if you do simulations, if you can see that easily. Yeah, okay. But now we want to give more microscopic confirmation of this conjecture, right, for this AHR model. But fortunately, in fact, AHR model is not to be exactly solvable. So I already mentioned that for stationary measure, there is a technique called matrix product method, which allows us to construct exact stationary measure. So this already indicates that there's something nice structure for this model, AHR. And in fact, one can apply the Bethe ansatz, as in the case of single species A set or TAS set, by which we can try to go further. Right? In fact, integrability for the AHR model was already shown by a guy named Cantini 10 years ago already. For general alpha and beta, but not Q. And then one can basically apply standard techniques like algebraic Bethe ansatz. Now the nested case, because there are two components, but there are standard procedures. But here I want to make one remark that so this is important. Somehow, so I believe that the Cantini have known the work of the stationary measure, and it can be constructed for general Q. But in his paper, he showed the integrability only for this special case of Q equals 0. So there is a question whether the general Q case is really integrable or not. So this is, almost strange, I think. But maybe, maybe you are good if you are good at showing about integrable systems. Maybe one can simply try to see if there's R corresponding R matrix for general case, and if you find R matrix, then you can write a paper. Yeah. Good. One paper is always good. Okay. And because we know the R matrix, one can apply the standard procedure, algebraic Bethe, and that's nested one in this case. And he did some calculation, the kind of starting point of the calculations. But we employ a slightly different version of the Bethe ansatz for our case. But anyway, we applied version of Bethe ansatz. I talked about this open, small open problem to many people, but up to now I haven't heard the success. So I'm looking forward to hear it. Yeah. I talked to Mangazel, I talked to Jingo, many people. Up to now I haven't heard the success. Right. Okay, so now we apply the data and dust for these two species assets. Maybe I don't have much time, so maybe I show only the simplest case of one particle case. So now we have only one plus particle popping to the, From here on, for a while, we introduce alpha and beta. Okay. So m is the number of plus particles, and m is the number of minus particles. So one particle case. So as usual, first we write down the mass equation, forward equation. When two particles are far away, it is easy. So this corresponds to the hopping of plus particle. This corresponds to the hopping of minus particle, and this is the escape rate. Of course, we have to be more careful when they are on neighboring sites. When they are at this order, from here, particles can swap their positions with rate 1. So this comes with coefficient 1. Now, so this configuration appears from the opposite order with a swap with rate 1, and the escape rate is alpha plus beta. So this is the equation we want to solve. And so this is the time evolution equation, and now we want to switch to the eigen equation. Then we replace ddt by lambda, right? So the eigenvalue lambda. So yeah, maybe you can write them down explicitly, but since I'm running out of time, so I want to skip some things. So the eigenfunction is again denoted by psi, as in the case of single species recip. Yeah, so now we have two species of particles, so this part has to be somewhat generalized from the single species case. And in this case, even though we have two particles, because they are different component species, we don't have A1 kind of exchange, sum of exchanges, and we simply try to use this ansatz depending on the order of plus and minus particles. And this you can try. This is just the ansatz, right? So if this is not enough to solve this equation, we can try some more complicated things, but it will turn out to be enough for this particular case. So basically there are three equations which we want to solve with these ansatz. From the first equation, one can determine this eigenvalue lambda, as in the case of single species case. And this is easy, seen to be given by this. If you recall the case of single species Heisef, this was the kind of one particle energy eigenvalue, and this is a two particle generalization. So this part is easy, and if you plug this ansatz to the second one, and with this lambda on the left hand side, you see that so this has to be lambda. Right? So then if you compare, from here we see that for this simple ansatz to work, we have to take alpha plus beta to be equal to 1. And as I already mentioned, with this condition, the stationary measure is factorized. But as I also mentioned, in the paper by Cantini, he showed the integrability for general alpha and beta. And he used the kind of standard nested beta ansatz to construct eigenfunction. So they are somewhat different. For our particular purpose, this version of beta ansatz seems to be useful. But if we want to generalize, maybe we have to use his beta ansatz. Anyway, so this is the one reason why we want to put this condition. And from now on, because we want to use this version of beta ansatz, we again put this condition. And in particular, we again take alpha equal beta equal 1/2. And from the third equation, we see that this is a little bit similar to the condition of interaction for the SF case. That determines the ratio of the two coefficients, A12 and A21, right? In a somewhat similar way, this third condition determines the ratio of these two coefficients, A plus minus and A minus plus, in a simple way like this. Okay, so this is the, with this condition, so this is the eigenfunction already. So this is a very, very simple beta ansatz for our AHR model for this simple case. But in principle, one can try to use very similar beta ansatz for general number of particles case. for the general case, the expression is a little bit complicated. So we have to introduce some notation. So this is the number of i's or xi such that this is bigger than yk, case particle position. And then with this notation, one can write down the beta that's wave function in the following way. Yes. So this is the expression for the beta and wave function, which works for the general NN case. But yeah, this is already pretty complicated. But if you look for 2 minutes, it's not so complicated, I think. So first, this eigenvalue is very simple, right? This is just a combination of two species tacit, basically. And this part is also very simple. This is almost like single species tacit. If you recall one representation of the eigenfunction, yeah, weight under wave function for the single species tacit. Yeah, I think I wrote down this kind of expression explicitly. So this is also the tacit single species weight under wave function. The only effect from the interaction of plus and minus particles included in this product. But this product is rather simple. This is basically just a product of 1 over z plus w. Right? So in this sense, already this model seems rather nice and simple model in the sense that the interaction effects are just encoded in a very, very simple product. But still, for general n and m, we have to use this notation. Yeah, for general configuration of particles, we have to use this slightly complicated object. But there are simpler cases. The first case is that when we have, sorry. Yeah. So because we want to consider this initial condition, we first assume that initially all plus particles are to the left, all minus particles are to the right. Right? So we write it like this. So this is already assumed. Then for the particular case of non-changing positions, I mean, even at time t, there could be a situation in which all orders doesn't change. Right? At time t, still all plus particles are on the left side, all minus particles are on the right side. In this particular case, so there's no such I, right? So because no, yeah. So So yeah. So with this condition, always xi is smaller than y. So there's no product here. So now this is 1. So basically, in this case, eigenfunctions are just factorized for this particular configuration. This is simple, very nice, but this is not so interesting because we are considering the case in which orders have not changed at all. But there's another simple case in which now the order has completely becomes the opposite at time t. All plus particles are now, so, maybe I'll divide this way. All plus particles are on the right side, and all minus particles are on the left side. So total exchange case. In this case, so this is always n. So this product becomes the whole product always. In this case. Yeah, there's still some effects from interaction, but this is a total product. So this is very symmetric, and this looks like a nice special case, right? And this corresponds to our particular setting. Yes? Believe. Yeah. No, yeah, we can check the Green's function. And this is basically passive case, right? So uniqueness should be okay. And then if the Green's function is there, then that should be coming from all eigenstates. Yeah. Okay. So yeah. So next step is transition probability, Green's function. As in the case of phasors, it's really parallel, I think. Yeah. Sorry. For this. Yeah, for this particular situation in which, again, total exchange have happened, the Green's function for this configuration is simply given by this. So this is really, you can immediately see that this is really coming from here. And this is also the same as in the case of single species cases, right? Yeah. But anyway, yeah, so this is one formula. And then, yeah. We don't need this, yes, but we have the expression for the general case. general configuration. Yeah. Yeah, of course, this is a bit complicated too. Yeah. Again, yeah, up to now we have restored alpha and beta, but now, so now we have transition probability. So starting from general configuration x naught and y naught, and we have also final configuration. Then now we want to consider particular probability. That all particles, plus and minus, have crossed the origin. And this fits well to this formula, right? And yeah, as in the case of single species cases, what we should do is basically to take a sum of all possibilities of the final position. And in this case, we also have to consider the initial condition, because now we have random initial condition for the plus particle. And this is also easy, because the dependence on the initial condition is just z to the power xj naught and w to the power yk naught. Right? So one can simply take the geometric sum to consider the random initial condition, and then one can arrive at some double multiple integral formula for this joint probability. So yeah. Basically, this is the final formula of this lecture. Yeah. Once we have this expression for the Green's function, it is, yeah, as I already said, it's pretty easy to calculate this joint distribution, and the result is given by this formula. Yeah, again, this looks a little bit complicated, but not so much, in fact, if you focus on z and w. If you look at z part, this is exactly the same as the Hassett case with the density rho. And this part is easier. This is exactly the same as the single species Hassett case for step initial condition. And now we have some interaction phase, which is simply given by this whole product of zj plus wk, right? And yes, at this point, these contours are just small contours around the origin. And now we want to do some asymptotic analysis to show our conjecture. So this part was not completely easy, but in fact, it turned out to be not so difficult. What we do is first rewrite this contour to the kind of the other side by using Cauchy's theorem. So now we are closing around the origin, right? Yeah, so here there's a 1 over z, so there's a singularity here, but we switch to the other places. Then there are singularities at 1 over 1 minus rho, and possibly at infinity. And for the case we are considering, in fact, singularity at infinity is not there, so there are only 2 points here. And this is of course a little bit heavy, but this is single order pole, so we can simply take it. And in this way, yeah, if you're interested, if you want to see what kind of formulas are there, you can take a look at the paper. But if we take this pole, then we can rewrite this into two terms. So one is just becomes now only W integral, which is in the standard form, which I showed at the beginning. So one can do the simple asymptotics. In the second term, in fact, this is a Z integral, and this is W integral. And even though I wrote like this is a simple product, in fact, here we have this thing, product. So this is not really product at this point. But this is, because we have already taken the pole at 1 over 1 minus rho, this is only around 1. And so this is the most non-trivial part. We can argue, and this can be shown in fact, that all Zj can be replaced by 1 in the large D limit. Then one can see that this W integral is really in the standard form, as I showed at the beginning. And then the remaining Z integrals are also in the standard form, as I showed at the beginning. Then one can see that I1 from I1 you get F2 of S minus. And for I2, this is the same, F2 of S minus. For J, when using a kind of little trick, one can see that this is given by Gaussian distribution minus 1. Then if you combine this, you see that this gives us yeah. So basically, this is what we wanted to see. So this was the conjecture from nonlinear fluctuating hydrodynamics. And now by using this calculation, we could confirm that this product structure, including this trace rhythm distribution and Gaussian distribution, appears from microscopic model. Yeah. Yeah, so now I already have time, so I think I want to finish. Yeah, but let me mention that. Yeah, so this is just a single confirmation, kind of first confirmation of the nonlinear fluctuating hydrodynamics from microscopic dynamics. But there are many possible generalizations, right? We could try to generalize the parameters, initial conditions, and there are many things one can try. And of course, much more difficult problem is to try to prove the conjecture for Hamiltonian dynamics. Anyway, there are many interesting questions in this direction, I think. So they are mixed. I think around here I showed you that S plus, maybe S minus is something like N plus 2 minus rho minus some J plus T divided by some constant like this. So these coefficients come from the matrix R. Yeah. And yeah, so these kind of coefficients look pretty complicated, but they appear exactly in the asymptotic analysis. Yeah, so there are many things one can try to do. Okay, yeah, sorry, so it's already 5 minutes, right? So I want to stop here. Thank you for your attention. Okay.
Any more questions?
Okay, thank you. Thank you. Yeah, I also wanted to talk about the symmetric limit, but maybe next chance.